Hi, I'm Isaac,
Hi, this is Harry.
and our project is a solar cell monitoring system for GT solar racing. So, as the name suggests, solar cell performance is crucial to the performance of our vehicle, yet we previously did not have accurate measurements of individual solar modules. The zone level measurements that we had are not granular enough for a couple of important purposes, one being to debug which specific module is degraded or underperforming, as happens from time to time in like a real world environment, and the zone level measurements are also insufficient to accurately model and simulate our array performance.
To improve the accuracy of our simulation, the system will measure the voltage, current, and temperature at the granularity of solar modules and use those measurements to automatically recognize deviations from ideal performance to adjust the simulation accordingly.
Our solution spans the solar car, the team's telemetry server, and a user's computer. For each solar cell pair, we have one monitor board which transmits data to a BLE receiver board. This data is in turn transmitted to the telemetry server through LTE or directly to a local server instance running on someone's laptop via serial. The telemetry server will then use this data to compute characteristics of the solar modules and detect deviations from their ideal performance. This will cause the simulation runner to rerun the simulation software on a user's computer.
The PCB acts as a drop-in replacement for an existing board which connects a solar cell, as you can see on the upper half of the screen. And the completed soldered version of the board should look like this. However, due to the soldering difficulty of the NRF caused by insufficient solder pad area and the BLE module not working properly, potentially due to the usage of heat gun during soldering, we decided to replace it with an Arduino 33 BLE. So the board now looks like this. However, the new MCU does not have compatibility with the most prevalent one-wire library for the thermistor, and it took us way longer than we expected to finally manage to get a reading from the sensors. But still, one of the sensors keeps reading NAN, and the reading is accurate yet unreliable.
The solar car already has Bluetooth capabilities, fortunately. An ESP32 based board receives data from tire pressure sensors, and we were able to use this board to connect to our solar cell monitor and receive data using the GAP protocol. This board is notified when any of the characteristics advertised by the solar cell monitor for like cell voltages, temperatures, and so on change, and this change notification will cause it to transmit the information on the vehicle's CAN bus. At that point, another board is responsible for sending the data to the server using LTE. In addition, the Bluetooth receiver can bypass the rest of the vehicle's telemetry system by transmitting data over serial to a connected computer. In the video clip that is playing, this is essentially what is happening. The Bluetooth receiver is receiving data from the solar cell monitor and printing it to serial. This provides a convenient way to test the board side portions of our system without needing to install everything fully into the solar car.
Through some initial research, we found out that finding a perfect IV curve fitting model requires too much statistic knowledge, and it's beyond the scope of my knowledge in this class to accomplish this. Instead, the telemetry server now is based on the IV curve equation, and it will recalculate the n in this equation, which is the ideality. If you look at the equation, variables such as IL and I0 are usually provided by the datasheet of the solar cell. I provide an example of the current using solar cell, which is the Maxion Gen 3. You should be able to find out the VOs, the open circuit current, the short circuit, the open circuit voltage, and the short circuit current from the datasheet. What we're really interested in are the voltage, current, and the temperatures when the car is running. when the standard deviation of any mentioned parameters is greater than a certain threshold, the telemetry server will recalculate the average value of those parameters from the last 5 minutes and calculate n, which is the ideality of the solar cell again. This is based on the assumption that 5 minutes is short enough to use the average of those parameters. And this assumption has been backed up by the legacy data from previous races.
The simulation runner is a script that will periodically make HTTP requests to the server to determine if the solar cell idealities have changed, and if so, it will rerun the simulator in response. This video is demonstrating this process. Unfortunately, due to some of the issues mentioned previously, we were not able to do much end-to-end testing of our system. So unfortunately here we are replaying a request response sequence for demonstration purposes. Note how at the end the script receives values that have not changed from the last run, so it waits for some time, makes another request, and then since the value has still not changed, the same situation occurs.
So what we have gained and what we have yet to achieve. What we have now is the ability to take module level measurements of the solar arrays, and it allows us to observe if an individual module is underperforming and should be replaced. We can also refine the solar array model, which is crucial to our strategy team, and we can close the loop of simulation, driver cars, and evaluation. From this project, we also have several aspects that we need to improve. For example, we need to change the board design to be integrated with the new Arduino 33 BLE. The choice of a one-wire temperature sensor has proved to be the worst decision of this project, and it's probably better just to use a normal ADC thermistor. We definitely need to do more end-to-end testing, and I think the biggest aspect that we need to improve upon is that we are unable to verify how much the dynamic optimization helps with the racing strategy, since the race itself only happens once a year, and mock races are not good for concept proving due to large amount of shading from trees and lights on the road.
Naturally, there are many opportunities for future work. Since we currently use the measurements to infer one characteristic, the ideality of the solar cell modules, we would likely be able to see better results if we were able to build a full IV curve for a module. And in that case, we would likely be able to make better statements regarding the strategic value of the system. However, the fundamental idea behind our project is ultimately that we can improve our simulation by incorporating measured data. And this means that automatically updating the simulation inputs and then rerunning it is probably the most valuable component we have implemented. We can apply this idea to other systems of the solar car and leverage other types of telemetry data to improve various models. Additionally, there is ongoing work within the GTSR team to allow better integration between our simulator and the telemetry server that stores this data. And this will make it easier to implement such processes of adjusting simulation inputs in response to measured data. And of course, we would need to revisit our PCB design. We went into the project knowing that such revision would ultimately be necessary because the design trade-offs are different between coming up with a working prototype versus installing about 18 copies of a race revision board into the vehicle. As an example, our choice to power a board directly from the solar cells that connects to it is something that merits further analysis. And of course, our work exposed further changes that would need to be made. For instance, our solution to bodge in the Arduino Nano BLE module is not going to have good physical reliability as we have implemented it now, so we would need to update the design accordingly. And also, our use of the Arduino BLE module has similar concerns as the original NRF module regarding introducing a new firmware programming environment and tool chain to the team. And of course, due to the several issues we experienced, we would recommend that future designs use regular analog thermistors instead of the digital temperature sensors. This concludes our presentation. Thank you for watching.
Thank you.